Very good morning students, this is your physics teacher Sharma and I welcome you people back to my class. In the previous class we have learned the relationship between the amount of current flowing through the conductor and the potential difference across the conductor, and we have discussed Ohm's law. We have learned that according to Ohm's law, the rate of flow of charge is directly proportional to the potential difference across the conductor, and that is when we have discussed about the term resistance. We have defined resistance as the property of the material by which a material opposes the free flow of charge passing through it. Okay, and we also learned that it is denoted by the letter omega, Greek alphabet omega, and we call it as ohm. Now, these conductors are also classified into two types depending on whether they are obeying this Ohm's law or not. They are classified into ohmic conductors and non-ohmic conductor. First, let us discuss about ohmic conductors. See, if I plot a graph between the current flowing through the circuit along x-axis and the voltage along y-axis in volts, then if the graph plotted turns out to be a straight line need not necessarily be always starting from the origin or not always making 45 degrees. Even if it is like this, a straight line, then we call these as ohmic conductors. Why? See, at every point you can see, for regular interval of voltage, for equal change in voltage, there is equal change in the current flowing. Okay. On the other hand, if I plot a graph between the current and voltage, and the graph turns out to be like this, which is not a straight line. Okay. That means it is not obeying Ohm's law. It is not directly proportional. After a certain point of voltage, the amount of current flowing is more for a little change in the voltage. So this clearly shows that it is not obeying Ohm's law. So that is how we have classified conductors into two types: ohmic conductors and non-ohmic conductors. Conductors which are obeying Ohm's law are called ohmic conductors, and conductors which are not obeying Ohm's law are called non-ohmic conductors. Now, when does a conductor behave like a non-ohmic conductor? Now, for this, we need to look into the conditions of Ohm's law. See, Ohm's law is applicable only if the temperature is constant. So, constant temperature. The area of cross section, the physical features like area of a cross section of the wire, the thickness, should remain same. Okay. Constant thickness, and that material or the conductor should not be a semiconductor. For example, if we take elements like germanium, silicon, these are semiconductors. They behave like insulators at a certain point, and once the voltage is increased, it starts behaving like a conductor. So it should not be like that. Not only these, PN junction diodes, Zener diodes, these kind of things which we will be learning in your higher classes, those all behave like non-ohmic conductors. Also, if we take an electric bulb, initially the resistance of the electric bulb will be very low, but as the temperature keeps on increasing, the resistance of the bulb increases and the current flowing through that will be decreasing. So, a glowing filament of an electric bulb also behaves like a non-ohmic conductor. So, this is the difference between ohmic conductors and non-ohmic conductors. Now, let us try to know what are the factors which affect the resistance offered by a conductor. Okay, factors affecting the resistance. See, resistance is dependent on factors which are temperature, length of the conductor, area of cross section of the conductor, and nature of material. Okay, so these are the four factors on which the resistance of a material depends. Let us see first the temperature. How is it the temperature is affecting the resistance? Let me tell you how. Say this is a metallic wire which is a very good conductor of electricity. Now as electrons are moving, let us assume these are the ions. Now as electron is coming, it is trying to travel from one end of the wire to the other end. It collides with one of the ions. It bounces back, collides with another ion, bounces, collides, and it undergoes n number of collisions before it could come out of the other end. Fine. Now, if the temperature of this is increasing, if the temperature of this conductor is increasing, which could be either because of the external factor or the inherent. See, every time the electron is colliding with the ion, electron and ion are coming in contact with each other. Whenever two bodies are in contact with each other, there is friction, and whenever there is friction, there is heat produced, because of which these particles, these ions, will gain some amount of heat energy, and using which they will start vibrating more vigorously. Okay, and when they are vibrating more vigorously, that means their kinetic energy increased. The electrons would find it more difficult to go to the other end. And so what happens? It undergoes more number of collisions. More number of collisions, that means the electron is losing its kinetic energy. That means it is taking more time to travel from one end to the other end. Okay, if it is taking more time to travel from one end to other end, that clearly says that the current has decreased. The current is not flowing freely. The charge is not flowing freely. Remember, I is equal to Q by T. And because of the increased number of collisions, the value T has increased. And because T has increased, that means the time taken has increased, the current, which is the T value is in denominator, so total current is decreasing. So that is how when the temperature increases, the current flowing through the conductor is decreasing, which we can say the resistance has increased. Okay. Now coming to the second factor, length. Let us take the example of a hose pipe, the pipe which you use to give water to your plants. I have a pipe which is say 1 centimeter in diameter. I have connected it to a tap which can give me 1 liter of water in 1 second. That is issue. Okay. If the length of the tube or the hose pipe is say some 20 meter, are you sure that the other end of the tube also you will be getting 1 liter of water in 1 second? Definitely not. Okay, if I cut the pipe to 10 meters, it may not give me 1 liter of water in 1 second, but definitely it will be giving you more amount of water when compared to previous condition. Now, if I cut that to 5 meter, we see the water is coming at a faster rate. Okay. This is because the friction between the surface of the tube and the water. Okay, the tube, the inner surface area of the tube is offering some friction to the water which is flowing. So some amount of water stopped there. Only the water which is in the middle is able to move faster. The same thing is happening in case of a wire also. Okay, if the length of the wire is more, then this electron will have to undergo more number of collisions. When the number of collisions is more, the time taken will be more. When time taken is more, the amount of current flowing will be less. That means we can say the length is directly proportional to resistance, or resistance is directly proportional to the length. If the length of the conductor increases, then the resistance offered by the conductor also increases. Now coming to area of cross section, let us again go back to the same example. The example of the hose pipe connected to a tap which gives me 1 liter of water in 1 second. Now if the pipe what I have taken is only 5 meter in length and the diameter of the pipe is big, say 3 inches, okay, then the water would find it very easy to travel through this. Instead, if I use only 1 inch tube connected to the tap, the water may be gushing out, but the amount of water that is coming out will be less. Imagine somehow I have used proper adapters and I connected an aquarium tube to that. Definitely 1 liter of water will not come to the other end of the tube in 1 second. This clearly says that it is showing that when the diameter of the tube is decreasing, the speed with which the water is flowing is also decreasing. In simple, I can say the resistance of the conductor is directly proportional, length is directly proportional, and resistance of the conductor is inversely proportional to area of cross section. If the area of cross section is increasing, water is able to flow freely. Water is able to flow freely, that means the resistance is less. Okay, now taking these two into consideration, I can write the equation as R is proportional to L, R is inversely proportional to A. Combining these two relations, I can write R is proportional to L by A. Okay, the resistance is directly proportional to the length and inversely proportional to area of cross section. Again, to get rid of this proportionality symbol, I multiply with a constant. R is equal to rho L by A, where rho is the specific resistance or resistivity. Again, in physics, we just don't bring any term and say this is a constant I have taken. Every term we take should be a well-defined one. So it is on us to define what this rho is. I will make rho as the subject in this equation and I get rho is equal to R A by L. Okay. If the area of cross section is 1 meter square and the length 1 meter of the conductor. If the conductor I have taken is having an area of cross section 1 meter square and the length of the wire being 1 meter, then I get rho is equal to R into 1 by 1, which implies rho is equal to R. This shows that specific resistance or resistivity of a conductor is nothing but the resistance offered by a conductor of unit length and unit area of cross section. Okay, so this is a very important formula and this gives you the definition of specific resistance or resistivity. Numerical questions based on this formula are amongst the most asked.